Welcome to this video on fiber optic communication. In this video, we will be looking into optical amplifiers. We will be discussing about the need for optical amplifiers, what optical amplifiers are, their basic applications, the different types of optical amplifiers, and their principle of operation. When a signal propagates in an optical fiber, it gets distorted. Therefore, it should be amplified or regenerated. Regeneration requires the optical signal to be converted into electrical form, retimed, reshaped, and then converted from the electrical form into an optical signal. So this proves to be a limitation for high data rates and multi-channel signals. In multi-channel signals such as WDM, if regeneration has to be done, the signal has to be demultiplexed and the individual channels, the optical signal should be converted into electrical signal, regenerated, converted back to optical and multiplexed. So regeneration basically limits the data rate and also is disadvantageous in case of multi-channel systems. For long distance applications, single mode fibers are popularly used. And in single mode fibers, dispersion is less and the distortion in the signal is mainly due to attenuation as the signal propagates along the fiber. Therefore, there is no need for regeneration. Optical amplification is sufficient. Optical amplifiers, they amplify the signal in the optical domain itself. There is no need for conversion of the optical signal into electrical and back from electrical to optical signal. So as the signal propagates, the signal can be amplified in the optical domain itself. There are different types of optical amplifiers: semiconductor optical amplifiers, doped fiber amplifiers, and Raman amplifiers. We shall have a look at the basic operation of a general optical amplifier. So there is an active medium to which the input signal is coupled and the medium amplifies the signal. The amplification is carried out by either the process of stimulated emission or direct transfer of energy from the optical signal itself. So the active medium gets energy from the pump source. The pump source can be either optical pumping or electrical pumping depending on the type of amplifier used. So the signal propagating in the active medium gets amplified, getting the energy from the pump source, and we have an amplified output. First, we shall have a look at the general applications of optical amplifiers. In-line amplifiers. These in-line amplifiers are placed along the link of an optical fiber and they are used to boost the attenuated signal which has been attenuated as it had propagated along the fiber, and this amplifier boosts the signal and helps in long distance transmission. The next is the preamplifier. These amplifiers are placed just before the receiver and they amplify the weak signal that is received. The receiver introduces noise in the signal during the conversion of the optical signal into the electrical signal, and this causes degradation in signal to noise ratio. So the preamplifiers, by amplifying the signal, helps to suppress the signal to noise ratio degradation in a receiver. Next, the power amplifier. They are placed just after the optical transmitter and they boost the power level of the signal that is to be transmitted and help in increasing the distance of transmission. Next, the booster amplifier. They are placed before passive couplers and they are used to boost the signals in a LAN connection, and they help to compensate for the splitting loss and the coupling loss. So these are the general applications of an optical amplifier. They are used in the optical link itself to boost the signal that is propagating, or they are used at the receiver end or at the transmitter end. Next, we shall have a look at the types of optical amplifiers. The different types of optical amplifiers are semiconductor optical amplifiers, doped fiber amplifiers, and Raman amplifiers. The semiconductor optical amplifiers and doped fiber amplifiers, they work on the principle of stimulated emission. The electrons are excited to the higher energy state and these electrons emit a photon when they are stimulated by the signal photon. Whereas the Raman amplifier, they function on the principle of transfer of energy from one optical signal to another signal. So the energy gets transferred from the pump wavelength, which is at a lower wavelength, to the signal wavelength. there is no need for stimulated emission in case of Raman amplifiers. In stimulated optical amplifier and doped fiber amplifier, the stimulated emission principle is the same as that of the laser, which we have already seen on a video on lasers. But here it is lasers without feedback. Therefore, the signal only gets amplified, and the population inversion or excitation of electrons to the higher state level can be carried out by either optical or electrical pumping. In case of semiconductor optical amplifier, electrical pumping is done or current is injected to excite the electrons, whereas in doped fiber amplifiers, optical pumping is done. Doped fiber amplifier and Raman amplifiers, they can be connected to the fiber optic link, and they can be used as in-line amplifier or preamplifiers or power amplifiers. And semiconductor optical amplifiers can be used as switches and wavelength converters. Next, we shall discuss each optical amplifier in detail. The first, semiconductor optical amplifier, the construction of an amplifier. It has an optical cavity which is similar to that of the laser, but the end faces are coated with anti-reflection coating to prevent reflection of the optical signals. Therefore, the input signal, weak signal that is input into the amplifier, makes only a single pass in the amplifier and it gets amplified. Electrical pumping is done, so electrons in the semiconductor material are excited to the higher energy state using current injection method, and when a photon from the input signal stimulates an electron from the higher state, it goes to the lower state emitting another photon which is coherent with the input photon. Therefore, we have amplification of the signal. So the active medium in a semiconductor optical amplifier is an alloy of third and fifth group elements, and indium gallium arsenide phosphate is a popularly used active medium. By changing the composition of the active medium, the wavelength of operation or the wave range of operation of the amplifier can be varied. So this semiconductor optical amplifier is similar to a laser without amplification. The second graph shows the gain for various input signal powers. It is seen the gain remains constant for small input signals. So it's a small signal amplifier, and for larger values it decreases drastically. So the point at which the gain is 3 dB below the maximum gain is the saturation power. And after that we have the saturation region where the gain decreases drastically. The advantages are the semiconductor optical amplifier is easily integrable, so it can be easily integrated into the same substrate as that of optical circuits and devices. And power consumption is lesser compared to that of a doped fiber amplifier, requires fewer components and is more compact, and has rapid gain response. The advantage is that it can be used in switches and for signal processing applications. But the disadvantage is that this rapid gain response causes fluctuation in the gain for different signal formatting, and it also causes crosstalk in multi-channel systems. Next is the doped fiber amplifier, and in which erbium doped fiber amplifier is very popular. So doped fiber amplifier, the fiber material itself is doped with another element to make it function as an amplifier. So for operation in the SCL bands, silica or tellurium oxide is very lightly doped with rare earth elements such as thulium or erbium or ytterbium. And for O-band operation, fluoride based fiber is doped with materials such as neodymium or praseodymium. Disadvantage of fluoride based fiber is that the excitation power required is higher, and also fluoride is brittle and handling is a little difficult. The advantages of doped fiber amplifiers are different pump sources operating at different wavelengths can be used. The coupling loss when these amplifiers are coupled into the fiber is less. The device is simple and low dependence of gain on polarization. And a very important, it is transparent to signal formatting and data rates. Therefore, the amplifier can amplify signals of different formats and also at different data rates. And the gain response, it can be made constant by using gain flattening filters, and it is immune to crosstalk. So we shall discuss about erbium doped fiber amplifiers or EDFAs, which are very popularly used in the C band and which was responsible for WDM systems to become popular. In case of doped fiber amplifiers, optical pumping is used to excite electrons to higher energy levels. That is, the electrons, they gain energy from the incident photon and move to higher energy states. When silica is doped with erbium, 3 electrons from the outer shell of erbium are available for conduction. So we have an erbium ion Er3+. We shall discuss about the operation of erbium doped fiber amplifier using the energy state diagrams. So there are 3 states available: the pump level, the metastate level and the ground state level. And each of these states, it is not a single energy level. When erbium is doped in silica, the energy levels split and we have a band of energy levels due to Stark splitting phenomena. And these energy levels, due to thermalization or due to thermal effect, they expand and we have a continuous band of energy levels. So when discussing about the energy levels in a EDFA, we would be talking about the ions, erbium ions getting excited. So when the photon is incident, the erbium ion gets excited to the pump level, and this is an unstable state and it quickly drops down to the metastable state. The excess of energy is released as phonons or molecular vibrations, and from this metastable state, when the incoming signal photon stimulates the ion, it drops down, emitting photon of the same wavelength as that of the incident signal. And a single photon can stimulate multiple electrons, and therefore amplification is possible. It should be seen that the pump level is at a higher energy state compared to the lacing level. So the pump energy should be greater than the signal energy, and we know E is equal to h nu. That means the pump wavelength should be lesser than that of the signal wavelength. So this is pumping at 980 nanometers. We can also have pumps working at 1480 nanometers. Here the ion is excited directly to the metastable state. It falls to the lower level of the metastable state, releasing a small amount of energy. Compared to 1480 nanometers, 980 nanometer pump is preferred because this produces higher level of population inversion and less noise level. 1480 nanometer, as it propagates in the fiber, the loss is less, and therefore the pump can be located at a remote location, and 1480 nanometer is used for high power amplification. Some of the ions, they move to the ground state level on their own, emitting a photon, and this is called spontaneous emission, which contributes to noise. Similarly, a small fraction of the ions, they get stimulated to the higher energy level by absorbing energy from the incoming signal photon, and this is called stimulated absorption, and it causes loss. So we have pump wavelengths that can operate at 980 nanometer and 1480 nanometers, and due to these continuous band of the various energy levels, the emission wavelength is maximum between the wavelengths of 1530 nanometers and 1560 nanometers. Looking at the gain spectrum for EDFA, which has silica fiber doped with both germanium and aluminum, the maximum gain occurs for a wavelength of around 1536 nanometers, and for another 2030 nanometers the gain is sufficient. And the gain can be flattened using gain flattening filters. And the second diagram, it shows the gain for various doping lengths of the fiber and for various pump powers. As you can see, as the pump power decreases, the gain decreases within a shorter distance. This is because the pump power is not sufficient to excite the electrons along the length of the amplifier. Therefore, as the signal propagates, it gets amplified during the initial length of the fiber, and the unpumped state, the energy from the photon is used to excite these electrons to the higher state. As the pump power increases, this length over which amplification occurs increases. An EDFA system, it consists of the basic erbium doped fiber amplifier of certain length, and then couplers to couple the pump and the signal, and optical isolators, which prevents the signal from reflecting back into the system, and the taps to tap a fraction of the input and output signals and to observe the amplification. A single pump or multiple pumps can be used, and the pumps can be co-directional pumping. That is, the pump in the same direction as that of the propagating signal, or it can be counter direction in a direction opposite to the propagation of the signal, or a combination of both co and counter directional pumping called the dual pumping. Counter direction pumping gives higher gain and co-directional pumping gives better performance with less noise. And pumping at 980 nanometers is preferred over 1480 nanometers because of low noise and higher population inversion that is possible. Next, we shall look at Raman amplifiers. These amplifiers, they are based on the nonlinear effect of stimulated Raman scattering, or SRS. We have already discussed in detail in the previous video on nonlinear effects. So here there is no stimulated emission. The energy transfer takes place due to the interaction between the optical signal and the vibrational modes of the molecule of the material. So a pump signal, it interacts with the material and the energy from the pump material is observed and transmitted as energy in a longer wavelength. So this wavelength is called the Stokes wavelength. So energy from a shorter pump wavelength gets transferred to a longer Stokes wavelength, and the energy difference appears as molecular vibrations in the material. Unlike EDFA, where special fibers are required, where fibers are to be doped with the rare earth elements like erbium for EDFA, in case of Raman amplifiers, they operate on a standard fiber, but they operate when nonlinear effects occur. So for nonlinearity to occur, the signal strength should be high. When signal strength is high, the fiber acts as a nonlinear medium. Both lumped and distributed amplifiers are available. In case of lumped amplifier, a separate unit with a pump amplifier and a fiber of few meters length is connected to the optical link. In case of distributed fiber amplifiers, the pump laser is connected in the counter propagating direction at the receiver end, and it helps to amplify the signal, and the last 20-30 kilometers of the fiber link operates as an amplifier. And Raman amplifiers, frequency of operation is wide and they can be used in wideband optical amplifiers. As mentioned already, in a Raman amplifier, the power gets transferred from a lower wavelength to a longer wavelength. From a lower pump wavelength, the power gets transferred to a longer signal wavelength and the signal gets amplified. And this higher wavelength to which the power gets transferred is called the Stokes shift. This graph shows the Raman gain spectrum, and for a Raman pump that operates at 1445 nanometer, the maximum power transfer occurs for a signal at 1535 nanometer, that is the peak Stokes shift is for 90 nanometer difference. Several pump lasers can be used in Raman amplifier to obtain a wideband gain spectrum. But when several pump wavelengths are being used, the pump signals themselves interact with each other and the power gets transferred from a lower wavelength pump to a higher wavelength pump. So when designing such an amplifier with using several pumps, care should be taken to choose the amplitude of the pump signals for each wavelength so that the net gain spectrum is flat. This diagram shows 6 pump wavelengths that are being used, and as you can see, the power levels of each of these sources are chosen so as to get a flat gain response at the end. This block diagram shows a Raman amplification system. So 4 pump lasers are used. They are combined using a combiner and coupled in the counter propagation direction to that of the signal that is propagating using a WDM coupler. So the input signal, the power is tapped at the input and output to compare the amplification that has been carried out, and the signal as it propagates due to Raman effect, it gets amplified, and gain flattering filters are used to flatten the gain, and we get an amplified signal. We have seen erbium doped fiber amplifiers operating at the C band, and using special techniques they can be extended to operate in the S and L band, and similarly we have Raman amplifiers operating at different bands. Now in order to have wideband optical amplifiers, a combination of two or more EDFAs can be used, or Raman amplifiers can be used, or a combination of EDFAs and Raman amplifiers can be used. And they can also be connected either in a parallel configuration or series configuration, or a combination of parallel and series configuration. The first diagram shows parallel combination, where the input signal, it is split into the two bands, and the two different EDFAs are used in this example. EDFAs are used to amplify the signal in the C band and L band separately, and those amplified signals are combined again. The major advantage of this parallel configuration is that amplification at one band does not affect the amplification of another band, and the noise generated in one band does not get amplified by the second amplifier. And in order to facilitate the separation of the two bands or filtering of the two bands, guard band should be provided, and this guard band becomes unusable. The next is the series configuration, also called the seamless wideband optical amplifier. Here the signal is first amplified by one of the amplifiers operating in a specific band, and then it is passed on to the amplifier which amplifies signal in the next spectrum. The advantage here is that multiplexers and demultiplexers, these couplers are not required, so the cost is reduced and also the coupling loss is minimized over here. And we can also have a combination of the parallel and series configuration. In this video, we have discussed about optical amplifiers, the need for optical amplifiers, what optical amplifiers are, and their basic applications, the in-line amplifier, the preamplifier, power amplifier, and then the different types of amplifiers and their principle of operation, the semiconductor optical amplifier, dope fiber amplifier, and Raman amplifier. These are the references. Thank you.